Okay, teacher M here. We're going to talk about isomers of a different type called stereoisomers. That's what we got on here. So what we have here. We did another video on constitutional isomers. The stereoisomers could be cis and trans, and we see this in this lesson and also in alkenes. All ones containing asymmetric carbon centers or atom centers. So here we're gonna talk about mostly RNS, enantiomers, diastereomers, mesocompounds using RNS assignments. Few definitions here. Isomers, these are just compounds that have same molecular formula but different structures. Constitutional isomers are different in the way the atoms are connected as symmetric centers. This is where you have a central atom connected to 4 different groups. Like here, the central atom is carbon, but you might have even a nitrogen or a phosphorus. Chiral molecules, these contain asymmetric center, which is a center or the middle of a molecule surrounded by 4 different groups or 3 different groups depending on the valency of the central atom. Stereocenter is an atom with the interchange, is an atom at which the interchange of 2 groups produces another isomer, while stereoisomers are just isomeric molecules that have same molecular formula and sequence of bonded atoms like in constitutional isomers, but they differ in 3D orientation of their atoms in space. That's where we use wedges and dashes. We use hatched wedges bond or the block wedge bond, where this is away, pointing at the bonds pointing away from you. This is pointing towards you, towards your nose. Enantiomer is one of the 2 stereoisomers that might be formed up here that have mirror images of each other, but they are not superimposable. They are not identical, just like your hand. You open your hand, palm open, and slide it over. Your thumb will not lie on top of the other thumb. Diastereomers are just stereoisomers that are not enantiomers. They differ at least 1 chiral center. We will be looking at that. So to assign chirality that on an asymmetric carbon, that means to assign R or S, most of the time we use atomic number. If you have a bromine and a chlorine on the chiral compound, on the chiral carbon, on the asymmetric carbon, then bromine is gonna have first priority because it has a atomic number than chlorine, which has atomic number 17. The smallest group by rule should always be facing away. Like here, hydrogen is the smallest atom around this asymmetric carbon because it has the lowest atomic number, so it should have the hatched wedge bond or the dashed wedge bond. Okay, if you get atoms directly bonded to the chiral carbon like this carbon, if you get the atoms having same atomic number, then you have to keep following the bonds and track until you get a difference in the next set of atoms, then assign your priorities. Okay, so this is just different scenarios that you get that will help you define whether a compound is an enantiomer, the pair of compounds are enantiomers, diastereomers, or just the same compound if they have the same molecular weight, same atomic number of atoms in them. What I should point out though is when you get your assign your chirality and find that the priority is going like to your right, that's clockwise, then the assignment is R. But if your priority is going counterclockwise, then you assign an S. So if you're comparing compound 1 and 2, like down here compound 1 and 2, having same number of atoms, same everything, the difference being the edge at the dash, the hatched wedge bond around some of these R groups. If C1 of compound 1 here is R and C2 of compound 1 is S, and for compound 2 you get assignment of carbon 1 having an S and carbon 2 having an R, then the difference here is RSSR. This is clockwise, counterclockwise, counterclockwise, clockwise, just the opposite of all the asymmetrical assignments, configuration assignments. So that's going to be an enantiomer. Okay, and yeah, so that's it. That's how we do it. And remember, you could be having RR, then this should be SS. There's so many other possibilities of judging whether it's an enantiomer. Because what I'm saying, in addition to what I've written, if you have RR, then the other compound having SS, then that's going to be an enantiomer too. Diastereomers is where you keep one of the chiral centers constant, like this. C1s have the same, but C2 are different. That's going to be diastereomer. So there's a difference in at least one chiral center, asymmetric carbon. Same compound is where the assignment is the same. If for same compound, the assignment is same for both C1 and C2 in the two compounds. So like if you have C1 to be R for compound 1 and C1 to be R for compound 2 and C2 to be R for compound 2 and C2 to be R for compound 2, if you have C2 to be R for compound 1 and C2 to be R for compound 2, then you have all the same assignment. Then these two compounds in this situation gonna be same compounds. So you could have SSSS, RSRS, and all other possibilities you can get combination of this. Okay, so that's what we'll be doing today. Enantiomers, they should be mirror images and non-superposable, but we call that non-superimpossible. So these two molecules, if you slide over this blue molecule on top of this red molecule, you find this chlorine will be on this side and this chlorine the other side. So they are not superimpossible. They should be enantiomers because you have the same arrangement of atoms in space. Okay, so let's give assignments R and S chirality. Okay, now in this molecule, the only chiral carbon that we have in this entire molecule is this carbon right here. This is a chiral carbon, so I'm gonna put an asterisk. Chiral carbons must be sp3 hybridized. You should not have double bonds on them or triple bonds on them. It's just single bonds around them, and it should be 4, and the 4 groups around them must be different. So going this way is different from going this way. So this, and that's a method, this hydrogen, you have 4 different groups around it. This is asymmetric carbon. This guy is the asymmetric carbon. So you are given a method with a bold wedge, then that means the hydrogen sitting on that carbon should be hatched. A carbon must have 4 bonds around it because it has a valency of 4. But how do we assign R or S? Okay, so the best thing to do first for these molecules to determine which is the smallest one, of course, is the hydrogen. So go ahead and assign it priority number 4 because we have 4 groups around this asymmetric carbon. So we are looking for priority 1, 2, and 3. You're looking for priority 1, 2, and 3. So you're looking again for atoms directly bonded to the chiral, to the asymmetric atom, which is the carbon. You have a carbon there on the methyl, a carbon here, and a carbon there. But this carbon is bonded to a hydrogen. So this carbon is this carbon here, and that carbon, the next high atomic number atom bonded to this carbon is a hydrogen. So go ahead and write a hydrogen there. We are looking to see where there's a difference, a tiebreaker, who wins. So for this carbon here, you have it bonded to another carbon Okay, this carbon is bonded to another carbon, so we write this carbon here, and the other carbon is this guy. We put it here, but since you have a double bond, it's taken to as if this carbon is bonded to two other carbons based on the double bonds. So we put two carbons there. Okay, and now you see this guy was gonna be the same story. This carbon is bonded to two other carbons because you have a double bond to this carbon and the other carbon that might have been bonded by this second bond here. So it's two carbons. So you can't make a judgment to that point who among this and this wins. We know here the methyl, of course, least because these two carbons have an atomic number that the hydrogen, so the methyl should be number 3, priority number 3. So we're looking for priority number 1 and 2. So here you can't judge because the group on here circled in blue is the same as what's circled in blue. So we have to move one bond over. So at this point circled in green, you have this carbon, which is this guy over here, bonded to a hydrogen. But here you have this carbon, which is this carbon over here, bonded to a carbon and a carbon. So the next bigger atom bonded to this carbon is this. So you have a tiebreaker here. So that means this should be number 2 and this should be number 1 because it's bonded to another carbon other than the other carbon. So this wins. So this is gonna be priority number 1. So this will be priority number 1. This priority number 2. This number 3. Alright, so let's go ahead and assign the priority. So that's number 1 because this guy is this arrow way down, and this is number 2 because it's that way down, and this is number 3 because it's CH way down. Okay, so you go ahead and give your priorities. So you have number 1, arrange them on the plane, the 3 numbers, because number 4 is facing away from you anyway, you don't need it. So you have number 1, and then you have number 2, and then you have number 3. The asymmetric carbon is right in the middle. It's right in the middle right there. So you are going counterclockwise. So you're going counterclockwise. And so the assignment of this chiral carbon is an S. So the assignment is an S. So that's the answer. Right? So you have to practice. This is gonna be very easy when you practice. Don't be scared. Let's look at the next example. Now you need to assign RNS for the asymmetric carbons in the molecule. The first asymmetric carbon is gonna be this one. The second one is that one. Okay, so let's assign for this one to your left. This one, this guy here. You do the same thing. Hydrogen is the smallest member. You have a bold wedge of metal, so the hydrogen should draw it out if it's not shown with a dash hatched wedge bond. It's gonna be number 4 because the list of the carbon there, a carbon there, a carbon there. Remember, we are looking at atoms directly bonded to the asymmetric center. So now let's take this carbon in green and write the sequence down here to look for the tiebreaker to decide who gets number 1, 2, and 3. And the blue, let's use this one, and the red is gonna be on the carbon bearing the methyl. So that carbon is this carbon for the methyl. This carbon here, remember, each carbon must have 4 bonds around it. So this one has 2 hydrogens on it, and this guy also has 2 hydrogens on it. Okay, so you can already see methyl here. This carbon will be bonded to a hydrogen, carbons bond to a hydrogen, while this carbon is bonded to another carbon and the 2 hydrogens. So this other carbon is gonna be our basis because it has a higher atomic than these two hydrogens that are bonded sharing the same carbon. So we write the carbon here. Okay, same story with this carbon is this one, it's bonded to two hydrogens, and this carbon, remember we are not looking at the asymmetric carbon, that we know all these guys are bonded to that asymmetric carbon, so we are moving forward. So this carbon is bonded to another carbon, so that carbon is bonded to this carbon. Okay, so there you can now rule out the metal and make it number 3, priority number 3, because the hydrogen has low atomic number than this carbon, so give it priority number 3. Hydrogen is priority number 4 here, nitrogen is priority number 3, but who gets 1? So we move on, because you can definitely see that what I'm circling now, those groups are similar, so you can't make a judgment who wins. Okay, so that's why we have to move forward. So since we know that this carbon is that and this carbon is that, we have to move forward and see what next. Now at this point we have to move over to these two carbons and see the difference. So this carbon is bonded to two hydrogens, while this carbon is bonded to a carbon and a hydrogen. So this carbon is bonded to a carbon and a hydrogen, so we're gonna take this carbon to be priority over the hydrogen, we write it over there, while this carbon is bonded to two other hydrogens, so we write one of the hydrogens here. This carbon over here, that one is not considered, okay, for priority, since it is shared by the two sides, right? Okay, so we just finish here, this carbon and that carbon. So the carbon that started the entire sequence, this carbon here, is gonna have priority number 1, because this carbon gave you a break. You have a tiebreaker right there compared to the hydrogen one of these. And the blue will be priority number 2. So you have your sequence of numbers as 1, 2, 3. You're going clockwise. So you're going clockwise. So there are 2 assignments for these guys and R. And remember, our smallest group is facing away from us, so it stays an R. If we had a bold wedge here, like this wedge here for the smallest group, the true assignment will be the opposite of the R, which is S, but in this case it's facing away, so it stays as an R. Alright, so what about the other side? The chirality for the other asymmetric carbon, you could as well see. I'm gonna get rid of all these things, because we know this is an R. So let's work out the other one. So again, this one is shared because it's half the ring and half the ring, so we're not going to consider that. So let's just move on the way we started. So who will have a higher priority here? You have a carbon, okay, and a carbon and a carbon. But this carbon here, since you have a double bond, that carbon is taken as if it's bonded to 2 other carbons. And because you have a hydrogen, the hydrogen is like that. So we pretend that it's bonded to 2 other carbons. So let's assign priorities here. So you have a carbon, a carbon, a carbon. We can't make a judgment on that, but let's just draw sequences with different color codes over here, based on the atoms bonded directly to the asymmetric carbon. Okay, so in black you have a carbon that's bonded to 2 carbons before the hydrogen. So I'm gonna draw the 2 carbons. Okay, so down here you have a carbon that's bonded to a carbon and 2 hydrogens. So put a carbon in one of these hydrogens. Okay, we want to find number 3. And then here in blue you have a carbon that's bonded to a carbon. Okay, you have a carbon. Here you have a carbon that's bonded to a carbon and another hydrogen. So obviously at this point you find that between these 3, of course we know hydrogen is the smallest. So between these 3 carbons, that and that, the one having a double bond wins. And so we're gonna give it already priority number 1. We're going to give it priority number 1 because it wins over the other sets. Okay, so now this is out. So let's look for priority number 2 and 3. Start over again with blue. You have this carbon bonded to another carbon, and so you have that carbon, that's this guy, bonded to another carbon, and the other carbon is bonded to a carbon. Okay. Okay, while here, remember I'm just picking out the carbons because if you say this carbon is bonded to a hydrogen, then a hydrogen has lower atomic number than this carbon, so our priority goes to this carbon. So you have this carbon bonded to another carbon which is bonded to another carbon. Of course, you know you have a hydrogen here. Again, I don't care about this hydrogen because on this carbon you have a carbon and a hydrogen. This carbon wins. So here you have a carbon, okay, and it's bonded to another carbon, and this carbon is bonded to 2 hydrogens, because remember I'm not taking this because this is shared between this top part and bottom part. So this is where we get our break, okay, just based on these 2 guys. So this where you get your tie breaker. So the one in blue will get priority number 2 because the carbon has a higher atomic than hydrogen, and this priority number 3. And now your set of numbers, starting from the black, you get 1, then the blue, and then the green, and we are going counterclockwise. So that's an S. Okay, that's an S. Okay, but there's a problem. It's an S, yes, but the smallest group has a bold wedge. The rule is it should be dashed wedge or hatched wedge. So since you get an S according to assignment, the true assignment should be the opposite of S. It should be an R. So this one is an R. True assignment is an R. Okay. Yep. So that's how you assign priorities. But you should, the shortcut is in this case. I know here I told you that you have a double bond, so the carbon is second to be bonded to 2 other bonds, 2 other carbons. The shortcut is if this carbon is sp2 and these 2 are sp3s as they are, this should win. Usually hybridization should help you because sp will have high priority over sp2 and sp2 has high priority over sp3. Okay. All right. Good. Hope you're getting it. I know it's mind-blowing, mind-tiring, but you should be fine. Okay, you see this example, you have a chiral carbon, that's a chiral center right there. The smallest group is a hydrogen and it has a H bond. So you get a, if you get an R, the answer stays an R. If you get an answer as S, the answer should stay as S. But the thing is, you have a nitrogen, carbon, and carbon to assign 1, 2, and 3. This is sp2 hybridized carbon. This is sp hybridized carbon. So in this case, even without saying that this carbon is taken to be joined to 3 other carbons because of the triple bond, you can still use hybridization to prioritize. So sp will have higher priority over sp2, but the nitrogen has atomic number than the 2 carbons. Nitrogen has atomic number 7. Each of these 2 carbons has 6 atomic number. Hydrogen, of course, has priority number 4 because it has atomic number 1. So we give nitrogen the amine priority number 1 because the nitrogen has high atomic number than these other 2 carbons that are bonded to the asymmetric carbon center as the nitrogen. So this is priority number 1, the sp hybridized carbon number 2, sp2 hybridized carbon number 3. And remember, because you have a double bond, you can take it to be bonded to 2 other carbons. Obviously, a carbon that's bonded, taken to be bonded to 3 other carbons, has a high priority over a carbon that's assumed to be bonded to 2 other carbons based on the double bond. So there you have it. So the arrangement of numbers here is gonna be nitrogen number 1, sp carbon number 2, sp2 carbon number 3. We are going S. So we are going counterclockwise. 1, 2, 3. The 4, it's just like your steering wheel in your car. The axle is pointing out from you, but these 3 bars are almost on the plane of your dashboard. So that's what you are looking at. So you have 1 here, you have 2, you have 3. You are turning your wheel counterclockwise. Looks like you're making a left. You're making a left on a highway or something, or junction or intersection. So it's an S, and stays as an S because the H here has a dashed wedge bond. Okay, it has smallest group has a dashed wedged bond. Some people say hatched wedge bond. So it stays as an S. If we had it as a block bold wedge bond like this, then instead of S, the true assignment would have been an R. So you're getting the story, I know. So you need to determine the relationship between these 2 molecules. You need to determine the relationship between these 2 molecules, and you have 2 chiral carbons per molecule marked with an asterisk. How do you say that? Can you teach me, please? Asterisk. Okay. Alright, get to business. So the chirality of this carbon here is gonna be based on the atoms directly bonded to it, which are the carbon, hydrogen, and methyl carbon. So again, using color codes, this carbon is gonna be that, and that carbon is bonded to 3 hydrogens, so we can choose one of the hydrogens, put it on there, right? Okay, in green you have this carbon bonded to a hydrogen and 2 other carbons. So the hydrogen here loses to be shown on our list because it has lower atomic number than these other 2. So we're gonna put 1 carbon there and the other carbon there. So for this carbon, you have, for this carbon, you have CC and CC. For the blue, okay, that carbon, which is this carbon, this carbon here is this carbon, is bonded to a carbon, okay, and it's bonded to 2 hydrogens, so we choose one of those hydrogens. So you get a tiebreaker first with the method, getting the method to have priority number 3, because of course hydrogen has priority number 4 is the smallest of the 3 carbons attached to the asymmetric carbon. Then the green's gonna have priority number 1 because it has a carbon which has on the third series which has high atomic number than the hydrogen, because it has a carbon which has a high atomic number than the hydrogen. Then the blue is gonna have 2. So assigning numbers on our wheel, you have 1, which is the green, 2, which is the blue, and 3, which is the method, the black arrow. So we are going clockwise. So we are going clockwise, and that's going to be an R, and stays as an R because the smallest group or smallest atom bonded to the asymmetric carbon is hydrogen. It has a hatched dashed bond. Alright, so you do the same story for this other carbon on this side. This carbon in blue, it's that one, is attached to another carbon, that one, and this is attached to 2 hydrogens. So we choose one of the hydrogens we put on there. This is a methyl. It has a carbon and 3 hydrogens. So it has a carbon and 3 hydrogens. So we choose one of the 3 hydrogens not drawn here. You can draw them on your paper. You put it on there. So you have a tiebreaker even with the green, because the green has a carbon bonded to 2 other carbons. The same story that happened here. Okay, so you get, once you draw your series, you get a tiebreaker. The first tiebreaker here, where the methyl will have priority number 3 out of the 3 carbons, because hydrogen has priority number 4 here. We don't care about it. We need to determine R and S based on only 3 numbers, 1, 2, and 3. And the green carbon, this one, since it's bonded to 2 other carbons, gonna win over the blue, which is only bonded to 1 other carbon. So the green will have priority number 1. So you have 1 down there, 2 there, and 3 there. We are going R. Our smallest group on the asymmetric carbon has a bold wedge bond. It needs to have a hatched or dashed bond. So since we got an R here, the true assignment is an S. Okay, since the smallest group is block wedge, so the true configuration is an S for that one. Let's do the other lower asymmetric carbons. Okay, so this is the asymmetric carbon that we need to assign chirality on it. So it's gonna have 3 carbons around it. This carbon, that carbon, and this carbon, plus the hydrogen. Hydrogen is the smallest member, so you can go ahead and write a 4 if you wrote the 2 molecules on your paper. Now the next one is to find 1, 2, and 3. So the methyl, this is a methyl. Just draw out the carbon and 3 hydrogens, just similar here. We had a methyl in the previous slide. So we go ahead and write this carbon over there is bonded to another hydrogen. We just choose one of the hydrogens out of the 3. Those are called homotopic hydrogens because they're same chemical environment in space. The blue carbon is this one. It's bonded to 1 other carbon and 2 hydrogens. So we choose to write the carbon because this carbon has a higher atomic number than the 2 hydrogens sharing the same carbon with it. So put that carbon here. This carbon is actually that carbon. Okay, all right, and on top of that is bonded to 2 hydrogens, so we choose one of these hydrogens, we write it there. For the carbon above, we have that carbon in green, which is this carbon here. Okay, and that carbon is bonded to 2 other carbons. You have this carbon. Let me show you which carbon that is. I'm drawing in hash bond. And you have this other carbon. Okay. right? So you have a tiebreaker for the methyl here, making methyl priority number 3, because each hydrogen has lower atomic number than the 2 carbons. And then down here you have a tiebreaker because the carbon here has atomic number than hydrogen. You have a tiebreaker. So the green will have first priority. Okay, this carbon will have priority number 1, and then this carbon will have priority number 2, and the methyl will have priority number 3. We are going S, we are going counterclockwise. And our smallest group, hydrogen, has a hatched bond, so that's truly S assignment for this carbon. You do the same thing for this molecule. This is a sequence you get CH, and you get for the blue CCH, and for the green CCC. You get tiebreakers there and there. You're gonna get green as 1, priority number 1, blue as priority number 2, and the methyl as priority number 3. You're going S, it's S. So down here is S there, it's gonna be S here. Okay, so let's decide what's the relationship between these two molecules based on what we did in the previous slide and on this slide. So write down here compound 1 and compound 2. This is compound 1 and that's compound 2. The assignment here is R and S, and the assignment here is S and S. So compound 1 you get R and S, and compound 2 you get S and S. You see down here you have same assignment on the second carbon, S and S, but up there is reversed, R and S. So that's a diastereomer because you only switch one of the serial centers chirality. So those are diastereomers. So these two compounds are diastereomers and not enantiomers and not same compounds because you have one chiral center maintained as an SS and the other one switched. Okay, so let's assign priority on these molecules and compare them. Okay, let's work on these molecules. We have only one chiral center per molecule, there and there. Let's determine the relationship between these two pairs. What is the relationship between the two pairs of compounds below? Are they enantiomers, diastereomers, or same compound? Alright, so you have oxygen, that's the chiral center I said. Is a chiral center I said. And around it you have an oxygen, hydrogen, and 2 carbons. The oxygen has atomic number 8, the 2 carbons has 6, hydrogen has 1. So we go ahead and give the hydrogen priority number 4. Let's determine priority 1, 2, and 3. Now, draw the same map to find the tie. Oxygen will have priority number 1, so you are looking for 2 and 3 because you already know hydrogen has a 4. OH will have 1 because the oxygen has high atomic number. Because oxygen has higher atomic number than 2 carbons. So let's look for 2 and 3 priorities. So for this carbon here, it's a methyl, so it has this carbon is this carbon right here, and it's bonded to 3 other hydrogens. So we only choose one hydrogen to show. But this carbon is bonded to a carbon and 2 hydrogens, so we prioritize writing the carbon then the hydrogen, but we don't need to write the hydrogen because you already have a tie at this stage, carbon and hydrogen. So this carbon will have priority number 2, the methyl priority number 3. And drawing your map, you have OH in red as 1, you have the methyl in blue as 3, and the ethyl with carbon 2 in it as 2. So you are going clockwise, so it's an R, and it stays as an R because the smallest group of atom bonded to the asymmetric carbon has a dashed bond. Okay, here you do the same assignment just based on what we have. You see these molecules are similar. The OH will have priority number 1, ethyl will have priority number 2, and the methyl priority number 3. So you have the OH as 1, ethyl as 2, methyl as 3. You are going counterclockwise. You get an S, but there's a problem because this hydrogen has a bold wedge bond. So, and we know the rule is the smallest group should be having the dashed bond, or should be facing away from us, not pointing towards us, because this hydrogen is pointing towards us. So instead of S, the true assignment is going to be an R. So you have R, and the same molecule bond, molecular bonding. The difference is just the 3D arrangement of the OH and hydrogen. So since you're getting R and R, this is the same compound, the same compound. So the answer for the relationship for these two molecules, they are same compounds. So they have the same chirality, same bond, attachment of atoms, same molecular weight. The difference is just these two hatched and wedge bonds. Okay, so I'll let you work on this before I start working on it. I'm counting down from 3 for you to pause the video. 3, 2, 1. Ta-da! I'm giving the answer. Okay, so you have two chiral compounds here. You want to determine the relationship between these two molecules. Okay, so you have to determine R and S and then go from there. Alright, so for this carbon, for this asymmetric, so for this asymmetric carbon here, we know this is hydrogen priority number 4. The OH definitely should be priority number 1, because you're looking to compare OHCC. Oxygen has atomic number 8, so it wins, so it's priority number 1. So the question is, who is number 2, who is number 3? Okay, the sequence of this carbon, sorry, let me say, so the sequence of this carbon, you have the carbon itself, and then this carbon is bonded to an oxygen and 2 hydrogens. So we prioritize the oxygen over the 2 hydrogens to write on our list, because oxygen has a higher atomic number than the 2 hydrogens. And then after that, now we can write the one of these 2 hydrogens. Now for the next one, I'm gonna draw it in green. That carbon is still bonded to oxygen, hydrogen and nitrogen. So between oxygen and hydrogen and between oxygen, hydrogen and nitrogen, oxygen is gonna win, because oxygen has atomic number 6, atomic number 8, sorry. Nitrogen has atomic number 7. So we list our oxygen, and then for the next atom bonded to this carbon, the nitrogen has atomic number 7, hydrogen has 1, so we have to write the nitrogen. So here you have the tiebreaker. So this carbon will have priority number 2, and the blue will have priority number 3. Looking at the arrangement of numbers, you have the OH as 1. You have the other group and the blue like this. So we are going that way, and based on this asymmetric carbon which you are trying to determine, the smallest group has a dashed bond. So the assignment is gonna be R, because we are going clockwise for that one. Okay, all right. So for the next carbon, you can pause the video if you want, because I'm going to erase it to show the other workings. You know oxygen has higher atomic number than the carbon and nitrogen and hydrogen. So OH is has priority number 1, followed by nitrogen, because nitrogen has atomic number 7, carbon has atomic number 6, followed by carbon, then hydrogen. So the arrangement of numbers is, here is 1, 2, 3. We don't care about number 4, and we are going counter clockwise. So it's an S for now. Then you go back and inspect the smallest group, group 4. Number 4 has a bold dash bond. It's pointing towards you, so the true assignment is an R. So that means for the first molecule you have R and R, because here it's an R and that's an R. What about for the second molecule? Second molecule, starting at this point, you have 1 oxygen, product number 2 be nitrogen, product number 3 is carbon, number 4 is a hydrogen. Arrangement of numbers, it's just like that, the same way we assigned this chirality here. So don't say I'm going too fast for you. Don't complain. Okay, I know you're smart, that's why I'm pacing up. Okay, so this one, you're going clockwise, so you expect it to be an R, but don't conclude that yet, because the smallest group has a wedged bold bond, so the true assignment should be an S. Now you realize this part of the molecule is similar to this part of the molecule. Okay, so I'm gonna write the S down here for comparison purposes, because this S is gonna be that guy. Now for the second carbon, for the next carbon, we delete all the writing so that we can clearly see. For the next carbon, priority is gonna be the OH, just as we did with this chiral center, with this asymmetric carbon. And then the second priority, okay, the fourth priority is the hydrogen because the smallest. And now you can see this carbon between these two will have 2 and 3. This carbon is bonded to a nitrogen and an oxygen, while this is bonded to a oxygen and 2 hydrogen. So obviously this one that's bonded to nitrogen is gonna win, just to be sure that you get what I mean. So let's go with this carbon and write the list. That carbon is bonded to an oxygen and then a nitrogen, while this carbon, the same thing as we did, while that carbon is bonded to an oxygen then a nitrogen. You have a tiebreaker. Okay, so that means this will be number 2, priority number 2, and this priority number 3. So you are going 1, 2, 3. You're going this way, counterclockwise. And so that's an S. Then you go back and check to make sure a small member group has a white hatch bond, so that's true. So you have an S on the second on this carbon here. So it's S. So you have RRSS. So these two compounds are enantiomers, right? Because you have RR and SS. R is changed to S, R is changed to S. Yeah? So you're good. Those are enantiomers. Got it? Smart. That's why you need to like these videos, because you can't make this stuff up. Alright. So what of this set of molecules? I'm giving you so many examples, so when you get out of this video, you don't need to read a book. You don't need to. You'll be teaching people in the streets stereochemistry and chirality. But give me credit. Don't plagiarize. Alright, so for this compound, if you do your correct assignments correctly, just without writing, looking at this chirality center here, the hydrogen should have the bold wedge, so it's bonded to a methyl, and this carbon going this way. Again, I'll keep on telling you that carbon is not going to be considered because it's shared from the top and shared from the bottom. Now if you're just to follow the bond the way now, because you're pros, for the blue one, this carbon is bonded to another carbon and a hydrogen, because you see this group here is similar to that group. You can't make your judgment from there, and that's why you have a tie of C and C. But that tie will help you to make the methyl priority number 3, because methyl here you have a carbon which is bonded to 3 other hydrogens. So we choose to only write one hydrogen here, so it's CH. So you get a tiebreaker here, so methyl will have priority number 3 because hydrogen has priority number 4, and between these two, this carbon and this carbon are similar. You have CH2 there. Remember, you have 2 hydrogens there, you have 2 hydrogens there. You can't judge from that, so you have to move one bond ahead. So let's go to with the green. So you can't judge here, so let's move on. On this carbon, it's bonded to a carbon. Okay, it's bonded to a carbon. You are not looking at this because this is shared. It's bonded to a carbon and a hydrogen. So write the carbon, and if you want to go further, you can write the hydrogen. Well, this guy, because we wouldn't make a judgment on this carbon is this carbon, so we look at this carbon, find, okay, this carbon is this carbon, sorry, this carbon is this carbon, so we have to look at the next carbon and what is bonded on it. So this carbon is this guy and it's bonded onto 2 hydrogens, so we only show one. If you want to go ahead, you can show the next one, but the tie is broken at that point, so the green wins. So the green will have priority number 2, the blue will have priority number 3. So you're going 1. Oh, so the blue will have priority number 2. So the blue will have, sorry, for the green, sorry, okay, so you got the ties. So the green will have priority number 1, the blue will have priority number 2, green priority number 1, blue priority number 2, and the metal priority number 3. You're going clockwise, so it's an R, but your smallest group has a bold wedge, so the true assignment is an S, so that's why we write an S there. We do the same thing for this guy. You find that's gonna be an S, and the example of this where it's done, it's on this molecule, because that bond is just similar to this bond, right? So you do the assignment. You see, these molecules are all having the same molecular weight, same number of hydrogens, same number of carbons. So to save time, you can just choose where the bonds, like this bond, since you got it to be an S, this one should be an S without doing the same thing, because you're looking at the same molecules, same molecular structure, only difference in bond, wedge, and dashes. So for this method here, the assignment is shown by working on this one. So this method will be CH, the blue eventually gets CCH, and the green eventually gets CCC. Priority is given as 1, 2 for the blue, 3 for the metal. You are going counterclockwise, so it's an S, and then you check to see that your smallest group is a dash bond, so it stays as an S. So if this is an S, that should be an S. And at that point, you can already assign any other bond, because if this is a wedge and has an S, this should be, this dashed method should be an R, right? And that's shown on here for this one to get an R. If you're looking at this asymmetric carbon, this carbon here will have CCC after assigning, and this blue carbon here will have CCH. The metal, of course, is CH. You get a tiebreaker here, and you get another tiebreaker down here, so that the green, this carbon here, will have priority number 1, and then the metal, of course, has priority number 3, and then the carbon in blue will have priority number 2. Right, so you're going 1, 2, 3, you're going S counterclockwise. So because that's counterclockwise and S, the smallest group though here has a wedged hydrogen. Is a wedge, bold wedge hydrogen. So if you get an S, the true assignment should be an R. So since this is an R, that should be an R. Now you get, for this molecule, it's gonna be SS when it's done, RR, SR, RS. And the next slide is gonna give you information on which is an enantiomer, which is a diastereomer. But on this slide, obviously, this is an enantiomer. These two are enantiomers because you have SS, RR, right? And these two down here are enantiomers because you have RS and here is SR. Both chiral centers are switched. But what's the relationship between what we have vertically and diagonally? Next slide. Okay, so from the previous slide you have SS, RR, RS, SR. So these two are diastereomers because you switch this S to an R, keeping the other two constant. These two are diastereomers because, so these two are enantiomers. These two guys are enantiomers because you're switching both chiralities, S to R, S to R. These two again are enantiomers. That's what we talked about in the previous slide, because you switch the R to the S to the R. These are diastereomers because you keep the R's and switch this R to the S. These are diastereomers still because you keep the two S's, but you switch that S to the R. You got the point now. Thank you for getting it. Thank you so much for getting it. Make me cry. So go ahead and work on this slide for your own practice. Let's wait for me to mask this in right. Okay, now we can start. So for this next set, this should be a hydrogen with a block origin. This is a hydrogen pointing away. So priorities, this is 1, this 2, this 3. So you are going R, but the smallest group is pointed away towards you. So the correct assignment is S. And for this, the same thing, 1, 2, 3. You are going S, and the smallest group is pointed away already, so it stays on an S. So the answer here is same compound between these two. So you'll be asked to find chiral centers. So you need to look for R groups which are different. For example, here R prime is different from R2, Roman 2 is different from R3 and R4. So 4 groups around a carbon. So here you must be having a hydrogen. There you should be having a hydrogen. You should be having a hydrogen and a hydrogen. And remember, asymmetric carbons are what should be sp3 hybridize. That means you need 4 groups because you have 4 electronic groups in sp3 hybridized atoms. Okay, so you have to have 4 bonds. So that's an asymmetric carbon because going this way is different from going that way. Getting to a nitrogen different from the hydrogen. So we mark this with an asterisk. That's another asymmetric carbon. That's another one, and this another one. So you have 4 asymmetric carbons. To get the number of stereoisomers possible from this, that can be drawn from this molecule structure of cocaine, the formula you use is 2 to the power n, where n is the number of the number of asymmetric centers that you have. Like up in this example got 4, so it's 2 to the power 4. The answer is 16 possible ways of drawing this structure using dashes and wedges. Now again, this is another compound. The asymmetric chiral carbons, we are looking for the chiral carbons, not the nitrogen, for morphine, which is a very strong painkiller on. Okay, so we're going to show hydrogens where we need to that. So that means this carbon here is not asymmetric because the two hydrogens are the same things, but we know this is a chiral center, That too is chiral. This carbon here is also chiral. We have this guy here is chiral. That's chiral. Okay, that's not chiral, that's an sp2 hybridized carbon. That's sp2, 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 sp2. So looks like we only have 1, 2, 3, 4, 5 chiral centers, or 5 asymmetric carbons. So number of stereoisomers possible is 2 to the power 5. So it's 2 times 2 times 2. 2 times 2. 6. What's that? 8 times 4. Is it 32? I don't know. You know better. Should be 32. So there's 32 possible ways of drawing the structure of morphine. And let me mention one thing. This molecule is not symmetrical, so we don't need to subtract the number of stereoisomers possible. You'll see that in the next slide. These meso compounds. Meso compounds have internal plane of symmetry. For example, this molecule here has an internal plane of symmetry, so it's meso. And when you're calculating the number of stereoisomers possible, you have to subtract 1, for example. In some of the examples you see. This guy is asymmetric. I mean, this guy is a chiral molecule because it has an internal plane of symmetry. You can get an internal plane of symmetry. I can draw it in this way. So the hydrogen is oriented away. The metal is pointing towards you, and you can have 2 hydrogens and 1 in plane. So you can go ahead and slice this molecule into half, because remember, carbon atom, hydrogen atom, hydrogen atom. So the plane cuts across the molecule. See, this side is reflected on this other side. Carbon, I was saying, carbon atoms, all atoms are just spherical in nature, like tennis balls. So, or an orange, you can cut it into half. So you can cut the whole molecule into half. So this molecule has an internal plane of symmetry. Internal plane of symmetry. Symmetry. Internal plane of symmetry. And so it's meso. Okay, it's a meso compound, and you see this carbon here is not chiral because this side is same as this side. CH2 and CH2 is not chiral, so no stereoisomerism possible. Yeah? So 2 to the power 0 because there is no chiral carbon. So the only isomer that can exist here is 1, because 2, a number to the power 0 is unity, it's 1. It's 1. Okay, here you have an internal plane of symmetry. The upper part can be reflected below, but we know these are chiral center because going this way to this point is different from going this way to that point. So this 2 is chiral, so you have n equals to 2. Asymmetric carbons are 2 of them, but you have an internal plane of symmetry, so the possible number of stereoisomers will be equal 2 to the power 2 minus 1, because this reflection will kill one of the molecule out of the set. So you have 3 possible stereoisomers. This guy has no internal plane of symmetry possible anywhere. You can't draw a line here or this way. So the 2 asymmetric centers are valid, 2 to the power n, and this is not meso, but this is a meso. This is meso compound. So this is meso, this is not meso. because there's no internal plane of symmetry here. 2 to the power 2, the answer is 4. For this Fisher projection, you have an internal plane of symmetry right there, but there's no internal plane of symmetry in here because the aldehyde is different from the alcohol at the bottom. So this guy is a meso compound with 2 chiral centers there and there, because you have 4 different groups around this carbon and this carbon. So number of stereo isomers 2 to the power n, n equals to 2, so it's going to be 2 to the power 2, so the answer is 4. But since it's meso, the true answer is 4 minus 1, so it's going to be 3 stereo isomers. Because this guy is going to give you 4, but 2 of the 4 stereo isomers drawn are the same thing. You're probably going to get the same molecule compound with same RS assignment, so you have to take only 3 of them to be valid, to be completely different between them. Okay, this guy, we said it's not a meso. It's not meso. There's no internal plane of symmetry. No internal plane of symmetry. No internal plane of symmetry, so it's not meso, but we know we have 2 chiral carbons there and there, so 2 to the power n, 2 to the power 2, so you have 4 possible stereoisomers. Draw enantiomers for this molecule. This is really where I say organic chemist can be lazy. Haha. Because just doing this, I got my answer even without drawing Newman projection or the Sohos formula or Fisher projection. So you just switch, just draw the mirror image, put a mirror there, draw what's reflected. So same thing for here, I just reflect my stuff. Assume there's a mirror in there, in the middle of the 2 molecules. That's what you're gonna see. Very easy. So those are these 2 are enantiomers of these 2 molecules. Okay, I told you, just draw mirror images. I told you, Teacher M tells you, you don't believe him. So the enantiomer for this Newman projection again is just gonna be the mirror image, the same thing. So if you have the chirality inside this molecule, if you have the chirality inside in this molecule, it's just gonna be switched by doing a reflection of the Newman projection. All the groups are reflected this here. So this is the enantiomer of this Newman projection G provider. Alright. Okay. I feel like I've talked too much, but I know I've helped you a bunch. Please like, subscribe, holla, tweet, Facebook, Yelp, or whatever those things you talk about. IMO this channel to your friends. Ciao, see you. One Swahili word for you. Kwaheri. Can you say kwaheri? Kwaheri. Kwaheri. Thank you guys. Bye.